Hello everyone, I hope you are doing well. I just want to say congratulations to the class of 2024 on completing their chemistry exam today. I hope this exam went well and you tried your best. I want to say thanks to one of my students who sent me this paper. I had to talk to most of my students in my class and they said that this exam was great, but the multiple choice part was hard. Again, this is my first try on this exam and these are my suggested solutions. If you see any mistakes, please let me know and I'll have a look at them. I will take my time with, this paper to explain the concepts, of course, for next year's students who are doing chemistry. Like always, guys, if you guys want private tutoring or have siblings or friends who want tutoring in subjects like chemistry, specialist methods, or physics, you can always email me through this email. Let's smash through this video. Question 1. Photosynthesis is an exothermic redox reaction, endothermic redox reaction, exothermic condensation reaction, or endothermic condensation reaction. All right, so let's break it down. So let's go through deep detail here. So we know cellular respiration. What is cellular respiration? Let's write it down. Oops, that's not. So cellular respiration. So we know that cellular respiration is basically the combustion of glucose, or the breakdown of glucose. So cellular respiration is basically glucose, so C6H12O6, basically gets reacted with 6 oxygens and becomes, of course I'm not putting states because there's no need right now, and then 6 waters that come out, and of course 6 CO2s. This is your cellular respiration formula. When we actually twist it or reverse it, we actually get the photosynthesis reaction. Photosynthesis reaction. Now, it's important to understand, because cellular respiration is, again, the combustion of glucose, basically, the combustion of glucose, we need to be careful here. Because it's the combustion of glucose, what is the enthalpy change? Well, we know the enthalpy because it's combustion. The enthalpy change must be less than 0 because it's exothermic. So for photosynthesis, isn't it, like we said, we just flip. It's just a reverse of the cellular respiration formula. So if we just reverse this, like this, what would happen to the enthalpy change for reversed ones? What would happen to the, Well, we know what happens, of course. It flips. The enthalpy change flips, becomes positive. So it's actually an endothermic process. Photosynthesis is an endothermic process. So it's not A and not C. Okay, so is it a redox reaction or a condensation reaction? What do we mean by condensation reaction? Condensation means that does water come out as a product? Does it come out? Condensation reactions are like the formation of carbohydrates, fats, or proteins, or like the combination of amino acids to make proteins. Water comes out. As water comes out, this is what we call a condensation reaction. Now, in this case, photosynthesis, we can see straight away there's no water coming out. It's not a product. So it's not a condensation reaction. So it has to be a redox reaction. And it makes sense. It is actually a redox reaction straight away. You should realize this because what it is basically, like what we said, cellular respiration, let's go back to cellular respiration. Cellular respiration is the breakdown, cellular respiration is what's happening is that glucose is going through a combustion reaction. Like I said, in the exam, they can use another word for combustion. They say oxidation reaction. So glucose is going through oxidation, and this hence oxygen is going through reduction, yeah? So absolutely, it is actually going through a redox reaction because we have oxidation reduction. And so imagine just vice versa for photosynthesis. Of course, also this is going to be redox reaction. So that makes sense. Done. So 1 is B. Let me take my calculator, sorry. Yep, 1B. Question 2. Which of the following statements is correct? The oxidation of glucose is reversible in the body? Rubbish, absolutely. Remember, the oxidation of glucose is the cellular respiration formula. This is actually not reversible. Think of it, how? So in the human body, you can break down glucose, of course, to get energy, but imagine, reversing it. So basically what? If we take CO2 and H2O, we combine that and we form glucose. That's like what? We have photosynthesis. As humans, we use photosynthesis. No, it's not. It's plants. We lack chlorophylls. Absolutely doesn't work. This is not how it works. And also, it doesn't absolutely work. Think of it. The oxidation of glucose, think of it as a fuel. This is a fuel. And say it's like methane, and you're reacting of oxygen. Of course, it's going through a combustion reaction. you know how when we say it's not a reversible reaction, because think of it, can we take H2O and CO2 and combine them back and to form your fuels like methane? Then there's no existence of fossil fuels. That doesn't make absolute sense, yeah? I hope that makes sense. You cannot. It's not a reversible reaction. It just goes through one reaction and done. And so that's absolutely true. So A is wrong. It's not in the human body. We don't actually have a reversible reaction. The combustion of glucose provides less energy per gram than the combustion of hydrogen. We can check that actually. Going in our data book, what is the glucose? So glucose, so it's per gram, yep. Here it is. So glucose is right over here. It's right over here. And so what's of course that's in kilojoules per mole. To change it to kilojoules per gram, we just have to do this. So so glucose is how much? 2840. To change it into kilojoules per gram, we just have to divide it by its molar mass. We know glucose is 180, the molar mass, which gives me basically, what's 2840 divided by 180? That gives me 15 basically 7 kilojoules per gram. That's my value. Let me just rub this part. We don't need this part here, and yeah, just this part here. Let's put that there. There it is. What about, and instead, so it provides then the combustion of hydrogen. What about hydrogen? So hydrogen will also do the same. So going up is hydrogen's on top here. And yep, this is kilojoules per mole. Of course, you divide it by the molar mass, which is 1, which is the same value, which is 286. 286 kilojoules per gram. Let's come back here. Okay. So let's read it. The combustion of glucose provides less energy per gram than the combustion of hydrogen, which is true. You can see that it provides less energy per gram, absolutely, than hydrogen. So this is actually true. So B is your answer. Let's check why the other ones are also wrong. The oxidation of glucose is given by this equation. No, this is our photosynthesis reaction. Like we've said, look, the photosynthesis reaction. So nope, this is wrong. The combustion of oxygen occurs during cell respiration. Nope, absolutely. It's the combustion of glucose that is called cellular respiration. So wrong. So choose 2B. Next question. Question 3. Let's use a different color here. 0.5 moles of ethane and 100 grams of air, that is only basically 22% mass over mass oxygen, are injected into a combustion chamber. The equation of combustion of ethane is this. If complete combustion takes place, which reaction is in excess and by how much? All right. So let's get the mole of each reactant. So we know the mole of ethane is 0.5, but what about the mole of oxygen? Now be careful. This is giving me a hint. So this is saying, hey, 22% mass per mass. So mass divided by mass equals 22%, which is 0.2. What's the total mass of that air? We know that it's 100 grams of that air. So 100 times 0.22 gives me a mass of 22 grams. Is that, if I'm not mistaken, that's how you would... Yes, so 22 grams. Basically, we only have 22 grams of oxygen. That's what it means. So 22 of, mass of oxygen in 100 grams of air. So we know the mass of oxygen. Of course, we want the mole. So the mole of oxygen is, of course, the mass, 22, divided by its molar mass, which is basically 16 and times 2, which gives me 16 times 2. That gives me, basically, let me write it here. So the mole of oxygen is 0.6875 mole. Done. And we know we also have how much moles of ethane. The mole of ethane, so C2H6, is equal to 0.5 mole. Done. So let's do some calculations. Okay, we need to basically predict which one's in excess and which one's limiting. So let's just use one. To do that, we just actually use one as an example. Like, let's use this for calculations, the oxygen. So imagine I'm using oxygen for calculations. By the way, that's the same here. I don't like that when they use that. It's basically, this is the same as 3.5. Yep. So what I'm going to do is I'm going to try, so using oxygen as for my calculation, I'm going to try to calculate the mole of ethane that would be produced using this oxygen mole. So the mole of ethane using the mole, of course, of oxygen is what? How much can I, so if I'm going from there, it's 1 over 3.5. So what would that give me? So 0.0, so 0.6875 times 1 over 3.5. That gives me 1 over 3.5. That gives me a mole. So a mole of 0.1964 mole. All right, so beautiful. So we have that much. So using oxygen for my calculation, I get this much mole. What do you see? Can you see how this over here is actually the mole of my, ethane is actually higher than the mole using here calculated? This tells me that, this ethane is actually in excess. So basically, let's go right here. Ethane here is in excess. Of course, the oxygen would be then limiting. So limiting. Perfect. So your oxygen is limiting. So beautiful. So we know which ones. So reactant in excess, of course, is ethane. So we can take those out. And how much amount of reactant is actually in excess? All right, easy. Didn't we just calculate the how much actually ethane would react? And this is how much they've given. So there's a leftover amount. So what's 0.5 minus that 0.1964? That gives me what? So 0.5 minus that. That gives me basically close to 0.3, which looks like B is your answer in that one. Beautiful. Done. So question 3B. Oh, doesn't look too bad. Question 4. Let's have a try at this one. Let's use the blue color. Consider the following reaction. Okay, so that is basically, okay, it's a reaction, yep. Which of the following correctly identifies the oxidizing agent? Remember, the oxidizing agent is the one that's being reduced. So reduction. And the conjugate redox pair in the form of oxidizing agent / reducing agent. So oxidizing agent means like, okay, you basically, again, reduced one. I like to kind of reduction, and this one is oxy. Okay. Which one's the oxidizing agent? Really easy. Well, we just have to look at the oxidation numbers. Now, I'm going to look at the easiest one, which is this iodine. I'm going to look at this, to be honest, this iodine looks the easiest because here, you can see how it has a -1 charge. So here it has a -1, whereas here it's iodine 2, which has a 0 charge. So to make them actually kind of equal, you would have had to add an electron, a negative electron on the right to make them equal. So let me explain. Let me write this. So for example, if I had this iodine and it becomes iodine 2, because there's iodine 2, you have to put 2 iodines here. There's an overall -2 charge here because there's -1 here, but you have 2 of them, so -2. So to compensate, what I have to do is actually have to add 2 electrons here because, again, -1 times 2 is -2. Now, can you see how both sides are equal? There it is. This is my half equation. Now, this tells me what? This tells me that, because, the electrons are on the right, this tells me that iodine is going for oxidation. So iodine is going through oxidation. All right. So, we want the oxidizing agent, which is the reduction. Hence, this here has to go for reduction. Because remember, if this is going for oxidation, this has to go for reduction. Hence, it's our oxidizing agent. So it's not C or D. Perfect. Now, what is our conjugate redox pair? Okay, it's just these two here. Which one is it? Now, okay, we're starting off the oxidizing agent, which is the one that's being reduced. Looking at our equation here. So, can you see this over here? When you're putting this as a reactant, it becomes oxidized. So this one here is oxidized. I minus is oxidized, which is also known as, if it's oxidized, it's the reducing agent. Reducing agent. So it would be A, actually. Because can you see the reducing agent would be that one there. And hence, of course, if you flip it, it's going to be then, this one here is going to be our oxidizing agent. So there it is, A. Hope that makes sense. For A, perfect. Question 5. Let's have a look at this one. Yep, it's a galvanic cell. When the galvanic cell is operating, so is the total chemical energy increasing and electrons flow from half A? So it's talking about total chemical energy. Okay, so think of it. A galvanic cell, what's the main purpose of it? What it does is it takes chemical energy, and it converts it straight away to electrical energy. So wouldn't your total, wouldn't your total chemical energy decrease? Because if a galvanic cell is operating, your chemical energy is decreasing, hence it's creating electrical energy. So total chemical energy should be decreasing, so it's not B or A. Now, where do electrons flow? Is it like electrons flow to half cell A or half cell B? Easy. What we just have to do is we have to look at which ones, we have to look at our electrochemical series. So what do we have? We have this one over here. And of course, we have platinum, so that doesn't react. And yep, PB. So, all right. So let's go to our electrochemical series and see which ones are getting reduced and oxidized. Go up here. Okay. So we have this one over here. That's the one. And we also have PB, which is this one, PB to PB solid. The highest one is going to be reduced. So this one over here, it becomes reduced, hence becomes the cathode, which is positive. So this one over here, this half cell here, oopsie, becomes a positive charge. This becomes a negative charge. All right. Now, we know in galvanic cell that like electrons flow from negative to positive. So they'll go flowing for the, this way, which basically they're flowing through to half cell A. So it looks like C would be your answer. Yep, decrease and electrons flow through half cell A. Perfect. Next question, 5. This one, let's have a look at this. Consider the following half equations. So it's a half equation, okay, and we have the, looks good. A galvanic cell is set up using inert electrons and the following chemicals. Half cell 1, which is 1 mole, 1 mega acidified potassium, solution of potassium iodide solution, which is actually just this over here. Half cell 2 contains oxygen gas in an alkaline solution. All right, which of the following statement is correct when the galvanic cell is operating? Before we even look at this, let's look at what the equations are. So we know we already know the half 1 equation looks like this. What about oxygen? So oxygen in alkaline solution is which one? It's this one over here, isn't it? Isn't it right here? Because if you think about it, can you see how it's oxygen? And it's in an alkaline solution. It has OH ions, so it's that one. Now, what is the voltage? It's 0.4. Yes, it's actually less than this. So it means, okay, well, we know already some stuff. So what it is, it's oxygen. Let me write it down. It's oxygen gas, 2 waters, plus 4 electrons becomes 4 OH ions. Done. So, and yep, it has 0.4. Okay. So put that here. So it has a 0.4, positive 0.4 volts. Okay. So again, because this one has a higher voltage, this one's actually going to go through reduction. This one, reduction. This one here is going to go through oxidation. Perfect. So, yeah, of course, if this is going for oxidation, then what's going to happen is you have to flip these. So let me move these here. That goes right over here. Put that there and that there. There it is. So look, you can, because the electrons have to be on the right. Okay. So which of the following statement is correct when the galvanic cell is operating? Hydrogen gas is produced at the cathode. So remember, the cathode is where reduction occurs. Now, guess what? No, it's not. It's water that's being produced and also iodine aqueous. So not hydrogen is anywhere produced here. The oxidizing agent is IO3 and the reducing agent is O2 gas. So oxidizing agent is the one that's being reduced, which is that. And yes, that is true. This one's getting reduced. And the reducing agent, which is the one that's being oxidized, is O2 gas. No, it's not. It's OH ions that are basically getting oxidized, which is our reducing agent, not O2. So that is also wrong. C, the concentration of OH ions decrease at the negative electrode. Remember, the negative electrode is the oxidation one. And yeah, they will. You can see that because they are the reactant and they're forming, oxygen gas and stuff, this concentration would start to decrease. So that's not wrong. I'm going to put a tick on that. Let's have a look at the next one. The mass of the electrode in half cell 1 decreases. All right. The way that I know which one, what half cell increases in mass and decreases, what I do is just like to know where the electrons are flowing. So I know for a fact that half cell 2, let me write 2, is the before I'm kind of confusing myself. Okay. Let's just draw a really nice pose here. So we have half cell 1 here, half cell 2. Half cell 1 contains the potassium iodide, which is the reduction, which hence is positive, and this is our negative. Remember, in a galvanic cell, electrons flow from negative to positive. Hence, because electrons are flowing to 1, this one actually increases in mass. So the mass of electrode in half cell 1 decreases. No, it increases. That's also wrong. So it's actually C. So 6C. Not too bad. 7. Let's have a look at this. So in a galvanic cell, copper 2 ions are converted to copper metal. The mass of copper is the positive for each 0.5 moles of electrons is transferred in the cell is what? A really nice question. Wow. So we have copper, and it becomes copper metal. So of course you would add 2 electrons here. So we have how much moles of electrons? We have 0.5, and of course we can get the mole of copper, which is basically 0.5 times, it's a 1-to-2 ratio, so it's half, which gives you 0.5 times 5, which is 0.25 mole of copper, and we want the mass of this copper, which is that's 0.25 times the molar mass, which I don't know. What is the copper molar mass? Let's find that out. Okay, copper molar mass. Where's copper? Where would you... Copper's right over here. So 63.5. 63.5. 63.5, and that gives me what mass? That gives me a 15.875 grams, which gives me A as my answer. So basically 1.6 times 10 is basically 16 grams, so it's the closest one. All right, so 7A. All right, question 8. Let's have a try at this one over here. Consider the following statements about hydrogen fuel cells. The use of porous electrodes reduces cell efficiency. Rubbish. The porous electrodes have increased the surface area, hence increasing the efficiency. So this is absolutely wrong. As the ratio of the amount of hydrogen supplied to the amount of electricity produced increases, the efficiency increases. What? Wait. As the ratio, so it's a ratio. Division sign here. So it's a ratio. So of the amount of hydrogen supplied. So hydrogen supplied to the amount of electricity produced. So electricity produced increases. So this ratio here increases. The efficiency increases. Well, let's think about it. If this ratio increases, it means that the H supplied increases, whereas the E, the electricity produced, decreases. Well, wait. If your electricity that's produced is decreasing, remember the point of a hydrogen fuel cell, it's a galvanic cell. Its point is to make, of course, electricity. But if your electricity decreases, then it's inefficient. How is it efficient? How does efficiency increase? Rubbish. So also that one's wrong. So straight away, we can take, what do we call? Both are wrong, actually. So which of the statements about hydrogen fuel cells are correct? Neither, basically. So 8, is that right? Yep, neither. So 8. I'm just going to think, yeah, is that how you do it? Ratios? I think ratios, yeah, AD. Hopefully that's right. I'm not too sure with that one. The overall reaction in an alkaline ethanol fuel cell, or alkaline yuck, is shown below, which is that what amount of hydroxide ions reacts with 1 mole of ethanol at the negative electrode of a fuel cell? All right. See, the problem with this is, okay, now you would want to make a half equation, so you'd be this here forms that, and you'll make a half equation using, so C2H5OH becomes TCO2. This is where the problem is. If it was acidic conditions, you remember how you can add up H plus ions and H2O? These are easy to deal with. But when it's alkaline solution, you can add up, in this case, OH ions and H2O. Now, the problem is both have oxygens. So, it's going to be such a problem. You don't know which one to put. Should you put OHs on the left? That's where this creates a problem. But nothing is hard, because luckily they did actually give us a hint. They gave us this whole reaction. They gave us the overall reaction. Well, we know, of course, that the oxygen here, it gets reduced. Remember, it's a fuel cell. The oxygen gas gets reduced. So coming here, let's go back to our, up here. Let's go down here. Okay. Which one? Yes, it's actually the same as this one, by the way. It's this one. Can you see how it's alkaline solution and oxygen gets reduced? So let's write that equation down here. So O2 plus 2H2O plus 4 electrons becomes 4OH ions. All right. So done. Now, I'm going to make sure that these are the same. So, can you see how there's 3 oxygens? So I'm going to multiply everything here by 3. So that'll be 3. 3 times 2 is 6. This becomes a 6. 3 times 4, this becomes a 12. 3 times 4, this becomes also a 12. Done. And imagine, you remember how we said it was the C2 H5OH becomes this, the 2CO2. Yeah, so because you remember how these are going to cross out, like there's no OH ions in the overall reaction, so there would have been 12 OH here, because then you know how they would have cancelled out. So that's true. There would also have to be 12 electrons here, because remember these will have to cancel out. And because there's water here and there's only 3 waters here, then there had to be 9 water molecules on the right, because you know 6 would cancel out and there will be left out 3 here. So guess what? This is our overall reaction in the you know, for this. Look how easy that was by using yep. So if I added these all up, it should give me my overall value there. Yep, everything looks good. Just want to make sure. Yeah, perfect. So I'm just going to rub this out, and now I've got the actual half equation. I can calculate it. So what's the amount of hydroxide ion that reacts with 1 mole of ethanol? So 1 mole of ethanol, H5OH. You have 1 mole of it. So the mole of OH ions is what? Isn't it just the one mole of ethanol, and it's a 1, so it's a 12-to-1 ratio. So it's 12 divided by 1, so 12. 1 times 12, which is 12 mole. So basically, for every mole of ethanol that reacts, we form 12 mole. No, we react 12 moles of OH ions. Let's choose D. 9D, perfect. Next question, 10. Consider the following statements regarding fuels. Bioethanol fuel is sustainable because it results in a no net release of carbon dioxide in the atmosphere. Be careful here. They're trying to trick you. No, it doesn't. Now, you might think, yeah, you know, carbon neutrality, you know, bioethanol, yes, you know, when it combusts, it releases CO2, but because, the plants use photosynthesis and consume that CO2, of course, to create. So it's like this reversible cycle, but be careful, it's not that sustainable. It's actually not sustainable because there's overall, what about the transport of bioethanol? What about that? So for example, yes, we make yes, we form a lot of it. Yes, we form a lot of it. The problem is transporting it, the CO2 that's released from the cars. Like you're not, it releases CO2, by the way. There's actually, the thing about it is, overall, it is not sustainable. It's not it is kind of sustainable, but when it says no net release, of course there's a net release. Like it is the best one because there is some carbon neutrality, but overall, by saying no net release of carbon dioxide, that's actually a false statement. There is some release of carbon dioxide, of course, from the transport when you're transporting that fuel, there's so much, so absolutely be careful with that. That's in your textbooks, by the way. They always say this thing. They say, of course, bioethanol is, carbon neutral, but there's also, it's also not in some way because, for transport, all the other stuff, planting it, the amount of resources, it doesn't become sustainable. 2. Hydrogen peroxide, H2O2, can be used as an oxidizing agent in fuel cells. Well, let's check that, actually. So normally in fuel cells, so the oxidizing agent one is being reduced, which is basically normally our oxygen, which is this. Normally it's this equation over here. Where is it? So normally it's actually this equation over here. This is our what we would be using in our so normally in a normal hydrogen fuel cell, like a hydrogen fuel cell, this will be the one that will be oxygen gas is normally our oxidizing agent. And yeah, so they're saying, hey, can hydrogen peroxide be as an oxidizing agent in a fuel cell? That's true. Yeah, you can, because look here. You can actually, because it's all the same thing. Look, you're forming water. We have electrons. We have ions that we need, the acidic ions, and it's just it's just H2O. It actually can act. Why not? It can actually act as it has the same form as our normal oxidizing agent, which is oxygen. So why cannot hydrogen peroxide be used? It can actually, from this, looking from this, it can actually be used. Then we can say it can be used. Let's go here. So this one's actually ticking that. Which one for something regarding the fields are correct? So it's only 2. So 10B. Question 11. Iron is produced from iron ore using heat and reducing agent. Using hydrogen produced from fossil fuel as a reducing agent to produce iron is consistent with the concept of linear economy. Absolutely yes. Linear economy, if you don't know what those are, there's 2 kind of economies in the study design. There's linear and there's circular. You can go down to your data book and you see these 2 here. Linear means because we're dealing with fossil fuels. Remember, fossil fuels are non-renewable. You take those natural resources, you take them, We make them, we distribute them, we use them and dispose of them. Of course, that's what we do with fossil fuels, yeah? When you're talking about circular, it's talking about renewability. Like, for example, natural resources, we take them, we can make and remake them, distribute them, reuse them, repair them. So it's like a recycling thing. And of course, remember, fossil fuels are not recyclable. Let's be honest. So straight away, rubbish. It's actually linear, not circular. So yep, not concept of circular. That is correct. Next one, C. The United Nations Sustainable Development Goal 0. What the hell does it got to do with hunger and, iron ore produced from fossil? The United Nations Sustainable Goal developed sustaining cities and absolutely got nothing to do with that. So it's A. It is the concept of linear economy with that one. 12. The combustion reaction between butane and oxygen gas is considered irreversible. True. It's a combustion reaction. Yeah, like what we say. So because what? The forward reaction is exothermic? Absolutely, that doesn't explain why. Remember, some are endothermic and are not reversible. Like, that doesn't explain anything. Yeah, this one's rubbish. B, the products are less stable than the reactants. Actually false. It's vice versa, because if you break it down, when it's a combustion reaction, yeah, the products are more, so it goes like this, of course, in the products, which are, of course, H2 and CO2, are more stable. We know they are more stable than their fuel, which is like butane and oxygen gas, because they just want to react. So absolutely, this is false, because the products are actually more stable than the reactants. The rate of the reverse reaction is so slow that it can be ignored. Kind of true, actually. So you can say that, yeah, there is a reversible reaction, but if it's so slow that we can kind of reject it, yeah, that kind of explain it. I have no idea, so put a tick on that. An unlimited supply of oxygen will favor the forward reaction. It has nothing got to do with explaining why, yeah. You can also have limited supply of oxygen and you still it will still favor the forward reaction. It has nothing got to do with like explaining why it's irreversible. So C would be the best. And C, yes, makes sense. The rate of the reverse reaction is so slow that it can be ignored. Could be true, yeah. All right. Question 13. Consider the following energy profile diagram for a n-catalyzed gaseous reaction. A solid catalyst is available for this reaction. Okay, which of the following statements is correct? Before we do that, so this is the uncatalyzed reaction. So of course, catalyst will look like this. Let me draw it. It looks like this. Remember, it will have the same. What changes is the activation energy. So it's the same enthalpy change overall. Which of the following statements is correct? Adding the catalyst, to the uncatalyzed reaction will increase the energy of the reactants. Absolutely not. The energy of the reactants are all the same. Nothing has changed. Removing the catalyst from the catalyzed reaction will increase the rate of reaction. What? No. If you remove the catalyst, you decrease the rate of reaction. The point of the catalyst is to increase that rate of reaction. C. Removing the catalyst from the catalyzed reaction will increase the activation energy. And that's actually true. You can see that, yeah? So with the catalyst, you can see the activation energy over here is actually small, but if you remove it, you get a higher activation energy. So C is the answer there. What about D? Adding the catalyst to an uncatalyzed reaction will make the reaction endothermic. No, nothing got to do with that. You can still see it's exothermic, so rubbish. So question, what is it? 13C. Done. Question 14. Consider the following reaction. So, all right. So we can see that it's an endothermic with reaction conditions. So which reaction conditions would give the greatest yield of nitrogen dioxide? So this one over here. So we're looking at pressure and we're looking at temperature. And yeah, should we use high pressure or like small pressure compared to this? Okay, so let's talk about pressure. If you have high pressure, what would happen? Like use Lechalle's principle here. So imagine you're the system and someone increases the pressure. You're like, wait, someone's increased it. I need to find a way to decrease it. What way should I go? You would go left, backwards, because there's less moles compared to this, which has 2 moles. So if you increase pressure, it will decrease the yield, actually. So we want little pressure. We don't want high pressure, so it's not B or C. A or B, because it has high pressures. Now, what about temperature? Should we be using high temperature or low temperature? Because we know it's an endothermic, the energy is going to be on your inputting energy into the system. So imagine, again, using Lechalle's principle, let's say if you had high temperatures, what would happen? So if you had high temperature, means high energy, the system's like, hey, someone's put so much I have so much energy. I need to find a way to decrease it. So the way to decrease it is you go to the forwards reaction, because, you will form more of this and hence you will decrease its energy. So, and that's good. You're forming more of the yield that we want, the nitrogen dioxide. So increasing temperature actually increases it. So choose C. 14C. Not bad overall. So last question. So I'm going to do the second part hopefully today. So after this, I'm going to finish the second part. Yeah, because I don't want this video to be too long. An example of a homogeneous equilibrium is the decomposition of sulfur trioxide to form sulfur dioxide and oxygen gas. Some SO3 is placed in an empty container, which is then sealed. Which of the following statements is true at all temperatures when the sealed system reaches equilibrium? Be careful, all temperatures now. So the temperature is not kept constant means the K value changes. You remember your equilibrium constant changes. That's okay. So let's write the reaction because I want to kind of wait. The mass of SO2 is 4 times. Okay, yeah, we can actually. The mass of SO2 is 80%. The amount of okay. What I'm going to do first is going to write the equation for it. So we have SO3 breaks down into SO2 and oxygen gas. So you need to put 2 here. So if I put 2 there, now there's 3, 6. There's 6 here. Yep. Now it's properly done. So let's have a look at the first one. The mass of SO2 gas is 4 times the mass of oxygen gas. Now be careful. We just want to be careful with this. Now because we know K value changes because of the temperature. You remember K value represents the extent of a reaction. So how much of the reactants get converted into the products. So it really doesn't actually matter in terms of. Because you know how these two are both products, SO2 and oxygen gas, these are both product, yeah. So let's say even if the extended reaction is small. So it means that you're not forming a lot of products, but again, these ratios still hold. These ratios, the mole rate, these ratios over here still hold, these constants. So yeah, so let's try, does this, is actually 4 times, let's check that. Also, we need to check that. So in terms of ratio, so we can see that, what's the molar mass of oxygen gas? So the molar mass of oxygen gas is 32, of course, grams per mole. And this one over here has 2 oxygen, which is 32. And what is sulfur? So 1 sulfur molecule is what? Sulfur, where are you? So S. There it is, S, which is 32, what is it? 32.1. So plus 32.1, which is basically, like 64.1. So grams per mole. Now, let's have a look. So you can see that in terms of mole ratios, going from oxygen to this, it's double. It's actually just double the amount. But also don't forget, you also have this the mole ratios here. So for example, let's actually do a question. This actually works. Yeah, it actually works. So for every, let's say we had 1 mole of oxygen gas, yeah? Let's say we had 1 mole of it. What you would do is, let's really do a calculation. If we had 1, because we're talking about mass here, let's actually use mole, and then we're going to do a real example. Wait. So imagine you had 1 mole of oxygen gas, and you wanted to calculate the mole of, SO2. So the mole of SO2 would be what? It would be, of course, 2 times the amount, so it'll be 2, because it's 1 times 2, yep. So that's, okay, we've doubled it, and then you also, if you're getting from, you're converting it, getting the mass of SO2, you would, so actually let's do a question. I think I'm more confusing by explaining it like this. Let's do an actual equation. This actually works, because think of it, the mole here, the molar mass doubles, but also you have the mole also doubles, so that's like 4 times. So let me explain. It's better to do a question, I think, to kind of explain it much more easier. It does look confusing, to be honest. So say we had the mass of oxygen. Let's say it's 1, yeah? Let's say it's 1. Let's do all our calculations using this. So hence, the mole of oxygen would be what? Isn't it 1 over 6? Because it's 2, of course, it's 16 plus 6. So 32, which is 0.03125. And so, using ratios, we can calculate the mole of SO2, because it's just 2 times that. Times it by 2, we get 0.0625. Now, calculating the mass of SO2, you would take that mole, this times it by the molar mass, which is, what's 0.62 times 64 times 1? Times 64.1. You get 4 grams. Think about it. So, for using 1 gram of oxygen, we formed 4 grams of SO2, which is true. This statement actually holds to be true. This holds to be true. And you can use it for any example. Yeah, you can put 2 grams and it still holds true. Let's look at the next one. The mass of SO2 is 80% of the mass of SO3. Let's check that one. Now, before we even check that one, actually, we need to check the mole. Before we do that, we need to check the how K value changes it, how it affects it, of course. So which one's that? SO2 and SO3. No, there's going to be a big problem. Can you see how one's a reactant and one's a product? And this is going to have a big difference, because if you're having those, your K value is going to change them, yeah. So for example, K value is the extent of a reaction. So imagine the extent of reaction is very small. It means you didn't form a lot of products. The reactants, most of them didn't, form the products. So if that happens, I think a lot of students might just straight away, do the same thing that I did using calculations. But be careful. These are actually, an extent of reaction is going to actually be important here. Because if some of the reactants, most of the reactants didn't form the products, you're going to have different amounts of moles and stuff. So this is not going to hold true. If you're going to play around with the temperature, which affects K values, the extent of reaction is going to be different every time. And hence, you're not going to form, it's not a ratio straight away, 80% of the mass is going to go all to that. No, absolutely wrong. Now, I think this is what they would have confused most of the students with this one, actually, is to think of it like this. What's the mole mass of this, by the way? This smaller mass is, I think it's 32.1 plus 3 times 16. The molar mass of this one's 80.1. Yep. Can you see how a lot of students be like, oh, okay, the mole to mole ratio is 1 to 1, of course, because 2 to 2, yep. And it's just, if I take this here, that 80 times it by 0.8, I get 64.1. So yeah, it works. Wrong. That's assuming that the they are fixed. The stoichiometric, the ratios are fixed. Well, they're not fixed here. Remember, because your K value changes those values. The extent of reaction is going to be different for all different temperatures. So yeah, it will affect the moles and stuff. So it absolutely won't be 100%. Yeah. This is assuming that that they are fixed. They're not fixed, because now they're going to be variable due to the fact that we have the extent of a reaction. That's actually hard. Dang, that's really hard to actually look at. Yeah, that could confuse. The amount of mole of SO2 and oxygen gas are the same. So SO2 and oxygen gas, nope, they are absolutely not the same. Rubbish. The amount of mole of SO2 and SO3 are the same. You might say, okay, yep, like what we said, the ratios are the same, the stoichiometric ratios, but remember, K value changes those ratios, changes the extent of reactions. Hence, so for some different temperatures, you're not actually going to form the same amount of moles. So be careful with that one. That's really hard. I hope that's correct the way I did it, but that's really, really hard. I hope that makes sense. I'll do the second part later, but yeah, I hope this video finds you well and helps you understand some of the concepts. And yeah, good luck to all students. Bye bye.